Hi everyone and welcome back to PrepFusion. I'm Anish and today we will start with the lecture 61 of our electrical machines subject. So today we will be discussing mainly about the construction of not induction, electrical machine subject. Today we will be discussing about the construction of synchronous machines, that is the armature winding. Mainly we will be focusing on armature winding, and it will be a almost similar topic as armature winding of DC machine. So armature winding of DC machine and armature winding of synchronous machine are almost similar. Okay, there is not much of a difference. So I will highly recommend, if it is possible, go back and revise. Here also I will do the same thing. So mostly it like you will have two formulas, two three formulas. That is what you have to remember. That's it. Two three formulas. That is what you have to remember in this particular topic. Okay. Also, we will, that formula is winding factors. There are mainly two kinds of winding factor. One is the coil pitch winding factor, Kp, pitch factor, and one is the distribution factor, Kd. Okay, those two factors only we have to remember, and our induced EMF changes according to that factor. That's it. Nothing else you have to remember. Okay. So first of all, let's come to this part. What is it? This is just simply a coil, right? It is just simply a coil. Okay, and uh, each coil has two each coil has two conductors, right? This is one active part of the conductor, this is also another active part of the conductor. We have already discussed about conductors in DC machines, so I am not explaining it here again. Okay, conductor is the part in which takes participation in the conduction, right? In the conduction, this part will not come into action in conduction because only the flux lines will cut this portion. Okay, already have been discussed in uh, what do you say, in our DC machines subject, right? DC machines chapter. So here if I see that armature winding, the armature winding is the main current carrying component of a synchronous machine's stator, responsible for the electromagnetic energy conversion between electrical to mechanical domains. So basically the armature conductor is responsible. Why it is responsible? Because we know through the armature current flows Ia, and that current and the magnetic flux, right, interacts with each other to produce a torque. Okay, so now uh, so let's first discuss about a few basic terminologies, right? So first one is conductor. Conductor is the active part of the winding that takes participation in the current flow. So current will actively flow through the conductor, right? It directly interacts with the magnetic, so current will flow through here as well, but this portion of the coil will take part in the generation of magnetic torque. Okay, so that is what conductor is. Turn, a turn consists of two active conductors connected end to end. So this is a single turn, right? This is a single turn, 1T, and it has two conductors. So one turn will contain two conductors, two turns will contain four conductors. Okay, four turns will contain eight conductors. Okay, now coil. A coil is formed by winding one or more turns together. Okay, a coil is formed by winding one or more turns together. It can be single turn or multi turn depending on voltage and current rating. Okay, voltage and current rating. So a coil is formed by winding one or more turns together. It can be single turn or multi turn depending on voltage or current rating. So I can, like, this is a multi turn coil, right? Why? Because a single coil has multiple turns. This is one turn, this is another turn, this, so it has three turns. Okay, this has three turns, right? How many conductors it has? It has six conductors, total six conductors. So number of turns here will be three. Conductors, conductors will be six. Okay, turns conductors. And how many coils I have? I have only a single coil. This is a single coil only, right? It's a single coil, right? Both of them are single coil only, but this coil is multi-turn, so it has multiple turns. So here also I have a single coil. Number of turns is 1. It is a single turn coil. Number of conductors is is 2. Number of conductors is 2. Okay, so it's a like we have 2 conductors and it's a single turn coil, right? So yeah, that's it basically. So how many coil sides I have? So here I have 2 coil sides. Here also I have 2 coil sides. This left hand side and right hand side. So coil sides are basically each coil, regardless of the number of turns, has 2 coil sides. One on the left hand side, one on the right hand side. So these are placed in different slots in the stator. Okay, so there are slots where we place the coil sides. Okay, I will explain about slots just in the next, I guess in the next lecture. We will not discuss about slots. So slots are basically this, right? So if these are my slots. Okay, so here we have like slots, and each turn is placed in a slot. So here one of the turn will be placed, let's say this. So each coil side is placed in different slots. So this yellow coil side will be placed in one of the slots, and the green coil side will be placed in the other slots. Okay, I hope that is clear. Yeah, so here how many number of coil sides I have? 2. Coil sides will be 2 only. And here my number of coil sides will be 2. Okay, so now let's discuss about multi-layer windings. What do I mean by multi-layer windings? So basically each slot is there. These are my slots, right? So in a single slot, if only single layer of winding is present, right, on a single, like this winding is wound, right, and a single layer, this is a single layer of winding is present, that is called a single layer winding. In single layer winding, each coil houses only one coil side. So only one of the coil side will be housed in a single layer winding. Okay, in a double layer winding, each slot contains 2 coil sides, right? So let's say this is one coil side, let's say this is coil C1. Similarly, I will have another coil C2. That coil side also can be placed in a single slot. Okay, that is what multi-layer winding means. So what are the advantages and disadvantages of multi-layer and single layer winding? Okay, so in as a result, the total number of coils is half the number of stator slots. Why is it half? Because each slot houses only one coil side. Okay, so I am able to house only half a coil in a slot. How many number of total slots I will require, right? So what do I mean? So let's say I have 2 coils. How many coil sides I have? 4 coil sides. So how many slots I will require? Here in case of single layer winding, each coil side will be placed in a slot. So I will require 4 slots. So basically for 2 coils I require 4 slots. So for C coils I will require 2 into C slots. So number of S, right? Number of slots will be 2 into C. Okay. So from here I will be able to get my total number of coils. What will be the total number of coils? Total number of coils C will be S by 2. That is what is written over here. Number of coils is equals to S by 2. Now one more thing is there. So how can I find out slots per phase? So generally we run 3-phase machine. So slots per phase will be total number of slots divided by the number of phases, that is 3. So S by 3. Slots per phase will be total number of slots divided by 3, that is S by 3. Okay. Coils per phase. Coils per phase will be uh, slots per phase is S by 3. Coils will be half of slots. So S by 2 by 3. So S by 6. S by 6 will be my coils per phase for a single layer winding. Okay, this type of winding is simple and effective but offers less flexibility because the distribution is not better, right? We will discuss about distribution and coil span later as we move along. So double layer winding, same, right? Two layers will be there. So now two layers are there. So each, if I have two layers, so I know one coil consists of two coil sides, or let's say I have two coils. Let's say I have two coils. Okay. So how many coil sides I have? Four coil sides. And each slot will contain two coil sides. So how many slots I will require? Two slots, right? So for two coils I require two slots. For C coils I will require C slots. So that's why number of coils and number of slots are equal here. Again, number of slots per phase will be S by 3. Coils per phase will be S by 3 only. Same, it will be same because number of coils and number of slots are same in case of multi-layer winding. Okay. So this is the most important part. Few things you have to keep in mind. No need to remember, but understand conceptually what are we discussing about. Okay. So now, like this already I have discussed in DC machines. Okay. Already have discussed in DC machines. Again, I am repeating. Okay. So this is already there. This we don't need to discuss. This has already happened. Pole pitch. What is pole pitch basically? Pole pitch is basically means the deviation of angle, like distance, angular distance between two consecutive poles. The angular distance between two consecutive poles is known as pole pitch. Okay. So already I have proven it in DC machines, so I will not explain it over here again. That we know electrically the angular distance between two poles will always be 180 degree electrical. How can I find out mechanically? We know this relation, theta is equals to p by 2 into theta m. Then I will be able to find out my mechanical angle. So here if you see, it is a 4-pole machine, right? So physically actually what is the pole pitch? In terms of mechanical angle, it is 90 degree. I can easily observe it is 90 degree, right? So if I use this formula, can I find out theta I? Theta I will be number of poles. I have 4 poles, so 2 into theta m, that is 90, that is 180. So whatever you do, you will always get theta I to be equals to 180 no matter what. 180 no matter what. Okay. So yeah, that is the thing over here. Yeah, I hope you have understood. So pole pitch is the angular distance between the centers of two adjacent poles. In electrical radiance, it will always be 180 degree electrical or pi electrical radiance. Okay. So pole pitch, sometimes they define it in terms of conductors or in terms of slots. Pole pitch in terms of slots will be what? Number of slots divided by the total number of poles. So that will be the pole pitch in terms of slots. So slots per pole will give me the pole pitch in terms of slots. Also they will ask pole pitch in terms of number of conductors. So that will be total number of conductors divided by pole, number of poles. So it will be conductors per pole. So if your total number of conductors, so each coil will have how many conductors? Each coil will have two conductors, right? This one, two. Okay. So same here, they will give you, don't worry, they will give you the total number of conductors, they will give you the total number of poles, and from there you will be able to find out pole pitch in terms of conductors, or maybe they will give you the pole pitch in terms of conductors and you might have to find out the total number of conductors. That is also totally possible, whichever way they can ask. So these are the different types of pole pitch that can be asked. This we had already discussed in DC machines. Okay, same thing here is written. Pole pitch refers to the electrical angle. It is generally in terms of slots, it is S by P. Pole pitch in terms of slots is S by P. So pole pitch will help us in determining the coil span or coil pitch. Okay. So what do I mean by coil span and coil pitch? I will just explain in a second. Coil span basically means how much angular distance each coil will cover. How much angular distance each coil will cover. Okay, that is what you have to take care of. Okay. So yeah, so let's discuss about this. Where did I go? Here, pole arc. So first of all, what is pole arc? So pole arc is basically the actual circumferential distance occupied by a pole. So pole pitch is the distance between the two centers of the pole, but pole arc is the actual distance that the pole field pole will cover, right? Because it will provide some magnetic flux density. It will only cover this much region, right? It will not cover the other regions. It will only cover this much region, correct? It will only cover this much region. Okay, it will not cover the other regions, correct? So pole arc will be this much region only. Pole arc will be this much region only. Okay, so that is what my pole arc is equals to. So yeah, that is it basically. That is what my pole arc is. So let's say your pole pitch will be, let's say in this case, what is your pole pitch? Pi by 2, right? Because your pole pitch also defines what is the maximum distance single pole can cover. Okay, a single pole can at max cover 90 degrees. It can wholly cover a whole of 90 degrees. Okay, maximum it can cover 90 degrees, because the rest of the region will be covered by other poles. You can observe, right? Rest of the distance will be covered by other poles. So this pole can cover maximum 90 degrees. Okay, but of course it will not totally cover the whole 90, because if all of them cover 90, right, there will be problems. Mechanically there will be problems. There has to be, like, it will cover something less than 90. So that's why this will be pole arc upon pole pitch. Okay, so pole arc will be lower. Pole arc generally pole arc is lower than pole pitch. That's why the ratio of pole arc upon pole pitch is equals to 0.7 to 0.9. That's why the ratio of pole arc upon pole pitch is 0.7 to 0.9. Okay, so that is the case over here. I hope you have understood this portion. So that is what my pole arc is. Pole arc is actual distance covered by the each pole. Okay, and the ratio is known as pole arc by pole pitch. Okay, okay. This already have explained in the DC machine, so I'm not explaining it here again. I'm just quickly revising you things. Okay, please go back and watch the DC machines lecture. There you will understand it even better. Okay. A conductor is the active length. So what is conductor? We have already discussed. The active length that takes participation in the magnetic flux interaction and the current flow, right? Because north and south pole will be here. The like only this much amount of length will take participation in the field lines cutting the conductor and producing torque. This much will not take participation. So this is actually called overhang. This is present for mechanical stability. You will say, this is, sir, this is waste of space. No, it is present. There is a reason behind for it to be present. It is present for mechanical stability. Okay, it is present for mechanical stability. Now, so basically it is responsible for the part of the coil that is responsible for cutting the magnetic flux and inducing EMF. Okay, so okay, coil already we have discussed. Why am I discussing it over here again? Okay, this is already been discussed, right? Sorry. Okay, so now let's discuss about coil span. What does coil span mean? Okay, coil span basically means the distance between covered by the two coil sides. Okay, so coil span is the distance between the slots where the two coil sides are placed. So if I show you, right, where is the slots? So these are my slots, right? If you remember, these were my slots. So let's say in each slot, let's say it's a single layer winding, so a single side will be placed, correct? Okay, so basically the distance, right, between, let's say one of the coil side is placed here, other coil side is placed here, so the angular distance, that will be my coil span. So let's say if one of the coil side is placed here, other coil side is placed here, the angular distance between the two coil sides will be my coil span. Or visually also, how you can understand is, if I copy this, right, the distance between the two conductors also you can say is my coil span. Okay, so the distance between the two conductors, this is defined as coil span. Okay, so it is generally expressed in number of slots, right? How many slots are there between? So let's say here, what is the coil span? 1, because only one slot is in between. If let's say one of the coil side was here, other coil side was here, the number of slots will be, coil span will be 2. Okay, so full pitch coil is known, like there are two types of coil span. One is full pitch, another one is short pitch. So what does full pitch mean? Full pitch basically means when the coil span is equals to pole pitch, right? It covers, like coil span will cover the whole pole pitch. What do I mean by it? So here, right, if I show you, let's say I have a two pole machine. Okay, two pole machine I have. So north pole, let me copy this. Yeah, let me do this only. North pole and south pole. Okay, so two poles I have, so now if one of the coil side is placed, like there are two slots, right? So in one of the slots, this will be one of the side of the coil, in other slot the other coil side will be placed. Okay, so how many slots are there between, or what is the distance, angular distance? It is total, in case of a theta m, mechanically electrically both will be same here because number of poles is 2, so it is 180 degrees, right? That is the coil span here, because the distance between the two coil sides is 180 degrees, mechanical or electrical both are same. Now what is the pole pitch? Pole pitch is also 180 degrees here. So whenever the pole pitch is equals to the coil span, then it is known as the full pitched coil. Okay, it is called as a full pitch coil. And if let's say the coil span is less than the pole pitch, let's say the other side of the coil is placed here, and the other side is placed here. So what is the coil span? Coil span is, in this case coil span is 90 degrees, right, mechanical, but my pole pitch is 180 degrees. So coil span is lower than pole pitch, so it is called as short pitch. Okay, why we do short pitch? To improve our waveform and to eliminate harmonics. Okay, to improve our waveform and to eliminate harmonics. How? I will explain. Okay, I will not explain you theoretically. I will give you the formula, and there from there I will explain. Okay, theoretically it is not important, gate point of view. That's why I will not explain you much theoretically. Okay, so full pitch, when the coil span is equals to full pole pitch, then it becomes full pitch. Basically that means that both the sides of the coil will lie under opposite poles. If you see, both the sides of the coil are lying under opposite pole, north and south, opposite poles, right? Advantage: maximum EMF is induced because both conductors experience peak flux variation in opposite direction. So in case of a full pitch coil, so maximum flux, right? Because if let's say in this case this coil side is experiencing maximum flux, but this coil side is not experiencing maximum flux. Maximum flux is here, right? So what is the advantage or disadvantage? We will discuss that. So advantage is that it will observe the maximum flux. It will observe the maximum flux. Okay, that is what is written over here. So the peak value of the flux will be more here. So the induced EMF, right, EM, peak value of the induced EMF also will be higher than a short pitch coil. So the peak value of the induced EMF reduces in a short pitch coil, but here the peak value increases. Okay, but there are few disadvantages as well. So there will be more harmonics in a full pitch coil, more harmonics. So waveform will not be purely sinusoidal here. In a short pitch coil, there will be lower harmonics. Lower harmonics. Okay, lower harmonics. So yeah, reasons for using short pitch coils. So yeah, same thing. Coil span will be less than pole pitch. Reasons: reduces harmonics generated in EMF waveform. Okay, how? I will explain. Okay, I will not explain theoretically, but formula I will give. Right, there is a factor known as harmonic pitch factor. Okay, it is known as harmonic pitch factor. What is it equals to? So it is basically equals to Kpn. This portion is important, gate point of view, is equals to cos of n alpha by 2. Okay, so what will happen is I know my induced EMF E is equals to root 2 f phi into n. Yeah, this is the value, right? But also there will be a factor known as pitch factor. Okay, so the fundamental component will be this. So there will be harmonics, third harmonics, second harmonics won't be there. There will be third harmonics, E3, right? So E3 will be root 2, same value, but my flux also will be phi 3, the third harmonic component of the flux, and frequency also will become 3f. Okay, into n, basically number of turns, into Kpn, the nth harmonic, Kp3, because it is a third harmonic pitch factor. So let's say if I want to make the third harmonic component of the induced EMF 0, so I will make my Kp3 0. How will I make my Kp3 0? So basically I want to eliminate third harmonic totally. So this will be cos of cos of 3 alpha by 2 equals to 0. So when cos of 3 alpha by 2 will be equals to 0, when this angle is equals to 90, right? When cos theta is 90, then it is 0. So 3 alpha by 2 has to be equals to 90. So 30 into 2, 60. Alpha has to be 60 degrees. So if basically they are telling me that so what is alpha actually? I forgot to tell you what is alpha. Alpha is the coil span. Coil span, right? Alpha is the coil span. So this is my coil, and if this distance is 60, right, then I will be able to totally eliminate the third harmonics. Okay, but remember, if it is 60, right, for first harmonic, what will be this value? It is cos 60 divided by 2, that is cos 30. So cos 30, right? What is cos 30? Cos 30 is root 3 divided by 2, that is 0.866. 0.866. So my induced EMF magnitude actually reduces. Although the third harmonic component is totally eliminated, but the fundamental component, the magnitude actually reduces. So that is a problem. That is a problem over here. Okay. So yeah, that is what my coil span is, and this is the most important portion. From this gate will ask questions. So this you have to remember. This also you have to remember. third harmonic component and fundamental component. Okay, so coil pitch and coil span already we have discussed. So here, right, what is the, it is a full pitched, basically the north and south poles, both of them are facing the coil sides. It is short pitch because opposite poles are not facing. So coil span less than 180-degree elliptical, because I know the distance between two consecutive poles is 180-degree elliptical. If the coil span is less than 180-degree elliptical, that means it is short pitch coil. If the coil span is equals to 180-degree elliptical, that means it is a full pitched coil. Okay, so that is the takeaway that you have to do. So advantage of short pitch is reducing harmonics. Also, it will save us copper, right? If the coil span is bigger, so I will need more copper for the windings. So it will save us copper, improves commutation. In DC machines, it will improve commutation. Okay. So these are the advantages. So this is the Corday angle. Corday angle in short pitch coil, the Corday angle is the angular displacement in electrical radians or electrical degrees by which the coil span is less. Okay, sorry, there I mentioned it wrong. Sorry, my bad. Sorry, this alpha, right, is the Corday angle. Sorry, this is not the coil span. I'm sorry. This is the Corday angle. I'm really sorry. Really sorry. Cording angle. Okay, this is the cording angle. What is cording angle? I will explain over here. Cording angle is basically the difference between the pole pitch minus coil span. So cording angle will be, pole pitch is what? Always 180-degree minus coil span. So cording angle always will be this 180-degree minus coil span. That's it. Cording angle will be always this 180-degree minus coil span. Okay, I'm sorry, alpha I mentioned there as coil span. Not, no, it is not coil span. It is 180-degree minus coil span. That is pole pitch minus coil span. Okay, please forgive me for that. Okay. Okay, so these are the things basically. Full pitch coil already I have explained. Short pitch coil I have explained. Okay, alpha is the angle by which it is shorted, also known as cording angle, and the formula I have written over here. Okay, so I guess this we don't need. This we have already discussed. This we don't need. So winding factors I have already discussed. That winding factor for pitch factor, it is known as pitch factor. This is the first winding factor, that is known as pitch factor, also known as coil span or cording KP factor. That will be ESP upon EFP. ESP is vector sum of coil sides that in EMF it will generate by arithmetic sum. This you ignore. This you ignore because this is not important gate point of view. Okay, ultimately this will be asked. This formula will be asked. Okay, and in EAC as well, this will be asked only. Okay, this I am not explaining because that will take the course even longer. I don't want to extend it because not important for gate point of view. Okay, so for nth harmonic, the pole pitch factor will be this cos n alpha by 2, where alpha is the cording angle. Alpha is the cording angle. Okay, so now let's come to the next topic, that is concentrated and distributed winding. Again I have explained this in DC machines. In concentrated windings, what happens is all turns of the windings are placed together in a single slot. In the same slot, all the turns will be placed together. Okay, of a coil side, all the turns will be placed together in a concentrated winding. I hope you remember what is number of turns. Okay, in distributed winding, turns are spread over multiple slots. So for the same coil, right, if I have multiple turns, so they are spread over. They are spread over. Okay, so how do I explain? So here I have multiple turns of coil, right? So this will be here, and here I will have another coil, here I will have another coil. So these different turns, right, actually will be placed in different slots. They will not be placed in same slot. So that is known as distributed winding. So what is the advantage? Advantage is, if I keep it distributed, I will get more sinusoidal like MMF. Okay, harmonic content will be reduced if I have distributed windings. Okay. But in concentrated winding, the construction will be simple. Simply keeping all of the turns in a single slot is easier, but harmonics will be higher here. Okay, it will produce more higher harmonics because all the turns are placed in the single slot, due to which there can be problem of harmonics. Okay, also the mechanical strength of this will be lower. Okay, have I told it? uh, this is already slightly distributed. This advantage of short pitch winding already has been discussed. This we don't need to discuss. This already has been discussed. Distributed winding. Yeah, this is what we're discussing. Yeah. So mechanical strength of this will be lower. Why? Because all of the turns are concentrated at a single slot. So overall mechanical strength will be lower for a single coil. If I distribute my coils in different slots, right? Mechanically more stable. This will be mechanically more stable. Distributed winding is mechanically more stable. Okay. So I hope you have understood the difference between concentrated and distributed winding. So concentrated winding is used in field winding of DC machine and of course in salient pole of synchronous machine. We have discussed, right? We use the concentrated winding in salient pole of synchronous machine. Okay, and your distributed winding is used in stators of the synchronous machine, stator, not in the rotor side, stator side, stators of induction machine and armatures of DC machines. So in these three places your distributed winding is utilized. So let's discuss this concentrated winding and distributed winding even better. Okay, so concentrated winding is this kind of winding where each slot has multi turns, no problem. One coil side will be placed in one of the slot, other coil side will be placed in other slot, and it will have multiple turns. Okay, all turns will be placed in a single slot. So if I want to define a new term I will define, that is M. M will be equals to what? M will be equals to slots per pole per phase. Okay, so here what is the slots per pole per phase? If I see, I have total 1 2 3 4 5 6 slots. How many poles I have? You see, 2 poles. I have 2 poles. How many phase I have? 3. That is equals to 1. So whenever this term M is equals to 1, that means the type of winding used is concentrated winding. What actually physically it means? Concentrated winding. That basically means that each phase will get the north and south poles at a time once. Okay, physically that is what it means. So when M is equals to 1, it means it is concentrated winding. Now there is one more term. Okay, that is beta. This is M, another term is there, that is beta. All these will be used in finding the distribution factor. So this portion is actually important. So what is beta? Beta, just hold on. Beta is basically the distance between the slot. Okay, beta is the slot angle or the displacement between the slots, or also known as the slot span. What is the angular displacement between each slot? That is my beta. How will I find it out? So for beta, it will be equals to, so I know one thing, right? Each coil, each pole span has 180 degrees. So if I am able to find out in each pole span how many slots are there, that should give me the beta. So what is slot span? Slot span means the angular displacement between each slots, right? I don't know what is the angular displacement between each slot, but I do know that angular displacement between each poles is what? Pi radian, pi electrical radian. And if I'm able to find out the slots per pole, okay, per pole if I'm able to find out, and if I divide that, so this will be slots per pole slots per pole into slots per pole only. If I'm able to find out the number of slots per, like what is per pole it is covering, if I divide that, that will give me the angular displacement between each of these. So let me take the example here, right? So here, how many slots are there between each poles? So total there are actually 3 slots, okay? So because it is half, so between here 3 slots are there and here 3 slots are there, okay? So slots per pole is 3, because how many poles I have? 2. How many slots I have? 6, right? So basically, what if, let's say, this formula was not there? If this formula was not there, what is the slot span? It will be total. I have 6 slots, that is covering whole 360. So 6 slots is covering 360. So the distance between each slot will be what? 60 degrees, right? So same will come out here as well. So pi upon slots per pole. How many slots I have per pole? 3 slots. I have 3 slots per pole. This 3 slots and these 3 slots. So this pi by 3 is 60 only, right? Pi by 3 is basically 16 degrees, pi by 3 in radians, right? So it is same. So this is 60 only. It is not different. So this formula is valid, but that is pi upon slots per pole. So this will be equals to pi upon slots per pole, that is S by P. So this will give me the beta, that is coil span, that will be useful. So there is another term known as phase spread, okay? Another term, that is xi. Xi is known as phase spread. What does this means? Phase spread or phase belt, sometimes it is called as phase belt, okay? So what does it actually mean? So it basically means that how much is the angular span covered under each phase under one pole, okay? So this definition is angular span covered by each phase under one pole. Okay, under one pole. So I know. So how will I calculate? So it's basically uh, how much angle does each pole covers? 180 degree, right? Between each pole, what is the angle? 180, right? So it is pi. So each pole covers 180, and in under each pole here, how many phase I have? 3. So how much angle does each phase cover? So this B phase will cover how much? Because each pole is covering total 180, right? So B phase will cover 60. A phase will cover 60. C phase will cover 60. So basically it is pi upon the number of phase, right? Divided by the number of phase, right? Number of phase. Now is this formula something familiar? So can I write my number of phase in terms of M, right? So I know M is equals to slots per pole. Slots per pole is here. If I multiply this, I have to find out the number of phase. Number of phase will be slots per pole divided by M, right? Slots per pole. So number of phase will be what? Number of phase, I can write number of phase will be slots per pole into M, correct? This is my number of phase. And what is slots per pole? So slots per pole is equals to pi upon beta, right? Slots per pole, I can write here, slots per pole is equals to pi upon beta. So I will replace my slots per pole here. So this will be equals to pi upon beta into m. So my number of phase okay, number of phase is equals to pi upon beta m. So number of phase is equals to pi upon beta m. So this I will replace here. This will be pi upon pi upon beta m. Okay, so this will be m beta. So my phase spread is actually equals to m into beta. For concentrated winding, it will be equals to beta because m is 1, right? Now these are the terms that will be used. So let's discuss the same for distributed winding. In distributed winding, you see the B phase, right? B dash. Okay. If it is multi-turn, so one of the coil side is B dash, other coil side is B. If it is multi-turn, I am placing all the turns in their separate slots. So now if I want to calculate M, what is M? M is number of slots per pole into number of phase. So how many slots I have now? So 3 here, total 3, 3, 6, 3, 9, 3, 12, 3, 15, 3, 18. So 18 divided by number of poles. How many poles I have? 2 poles. 2 into number of phase 3. So you are observing that you are getting 3, which is greater than 1. So for distributed winding, your M will always be greater than 1 no matter what. For distributed winding, your M will be always greater than 1. Okay. This is a property of distributed winding. Let's calculate the other values. What about beta? Beta formula will not change. Beta will be pi upon S by P. How it came, I just derived in the previous slide. So in this example, what will be pi upon S by P? So pi upon S, number of slots this time is total 18 divided by number of poles, that is 2. So it will be pi by 9. So beta has reduced. What is the phase spread? Phase spread will be m into beta, which will be equals to m is m and beta is this, right? So if I want to calculate, in this case m is 3 and beta is pi by 9. So phase spread is still same, pi by 3. So phase spread does not change, right? In case of distributed winding and in case of concentrated, each phase is still spreading 60 degrees. So these 3 slots actually are taking 60 degrees. But here all of the windings were concentrated in one place. All of the turns were concentrated in one point, but here it is distributed. So it will be more sinusoidal. But overall, the magnitude will be lower. Same like just like the pitch factor. Okay. Same just like the pitch factor. So phase spread will not change. Here also it is pi by 3. Here if you notice, here also it is pi by 3. M beta, beta we have just derived, that is pi by t. So m beta will be, in this example, m is 1 into pi by 3, that is this will be pi by 3. Okay, here also it is pi by 3. So phase spread will not change, but I hope you are now observing that how it is distributed, because all the turns are distributed. Now it is clear. Okay, everything is clear. Don't worry, everything will be clear slowly as you study the subject. Okay, so now there is a term known as distribution factor. So that is this KD. So distribution factor is the basically it is a ratio of the resultant EMF from distributed coils to the arithmetic sum of the EMFs. What do I mean? So here, right, as the turns are distributed, so the resultant EMF will be vector sum of all the induced EMF. It will not be a single EMF, because here it is a concentrated coil So all of the EMF will be produced here only, but here the EMFs are generated here in three different places. So there can be bit of phase difference. Okay, I'm not going into the theory here. I'm just telling you the definition. That's it. Okay. So if you want to learn more about it, please go through PSP Umra. I will not explain it over here because for gate point of view, it is not important. This much is important. So this topic is kind of formula oriented. So that's why I'm teaching it like this. The theoretical part is not important. Okay, that's why I will not explain this. Okay, if you want to look more into it, please go into PSP Umra. Okay, you can look more into it. But the formula for distribution factor will be this. Okay, basically if it is concentrated, then this kd will be 1. Kd will be 1. Okay, why, how is kd will be 1? So if I say that kd when it is concentrated winding, right, concentrated winding, so this will be equals to sine m. In case of concentrated windings, m is 1. So this will be beta by 2 divided by m. Here m is also 1 into sine of beta by 2 divided by sine of beta by 2. So this will get cancelled. So I will be left with 1. So kd is 1 for concentrated winding, just like the pitch factor. Pitch, in case of pitch factor, if it is full pitched, kp will be 1. So kd will be 1 for concentrated winding, and this is the formula. This you have to remember. Okay, no other option. This you have to remember. Of course, there is derivation. Many educators will derive it, but there is no point in deriving it because anyways you have to remember it. Okay, so it is sine m beta by 2 divided by sine divided by m into sine beta by 2. Okay, what was the pitch factor? Pitch factor was cos n alpha by 2. Very easy to remember. And what is the distribution factor? Kd, it is sine m beta by 2 divided by m into sine beta by 2. This you have to remember. Okay, if it is nth harmonic, so this is for the fundamental component, right? For nth harmonic, in place of m, n extra term n will be present. In place of m beta, extra term n will be present. So you see here n m beta by 2, here n beta by 2. So that extra term will be there for nth harmonic. For the nth harmonic induced EMF, this will be there. So overall, the winding factor Kw will be the product of the two factors Kp into Kw. So overall, your induced EMF actually is equals to root 2 f phi into n into Kp into Kd, two factors, which is equals to winding factor. We write it as a single factor only, Kw, which is generally less than 1, but it will be normally 0.866, 0.8, not that low value, but it will be 0.8, something like that. Okay, so yeah, I hope it is clear to you guys. So yeah, that's it basically. For a concentrated winding and full pitch winding, the EMF induced will be this. There will not be any what do you call, there will not be any reduction in the voltage. Okay, so here m will not be present. Why is m present? M actually is for the nth harmonic, right? No, m will not be present. Sorry, m will not be present. This is wrong. Only number of turns will be present. Now if it is not full pitched, then this Kp will be there, right? If it is not full pitch, so this is not full pitched. Okay, for distributed winding, if it is full pitched, it will be 4.44 into n into Kd, distribution constant, distribution factor, right? And if it is not full pitched, it will be Kp into Kd, that is winding factor. So m I have to remove, m will not be there, sorry for that. Okay, for nth harmonic, En, right? What will be the nth harmonic induced EMF? It will be root 2 pi into n into f into the number of turns into Kp into K, uh, Kpn into K dn. Remember, what was our Kpn? Kp1 was cos of n alpha divided by 2. Remember what is alpha? Alpha is the cording angle, right? 180 minus the coil span. So alpha, so this slide is the most important one. Okay, alpha was 180 degree minus coil span. This slide is the most important one. And what is Kdn? Kdn is sine of nm beta by 2. Okay, sine of nm beta by 2 divided by m sine n beta by 2. Okay, so this is my Kdn basically. This is my Kdn. Okay, so I hope you have understood this point. So I hope it is clear. So this slide is the most important slide. Okay, whatever we have discussed, for theoretically that is important, but this slide is the most important one. This slide will be used in the solving the numericals. So I will give you this numericals as a homework, and we will solve this numericals in the next lecture. Okay, this will be as a assignment homework to you. This a lot of questions are there. This one, then this one, it's the same question, is it? Huh? Okay, this is the second question, is it? Oh, sorry, this is the same question. So let me keep one only here. The same question, this one, then this one is the third one. This one, you can pause and try it out by yourself. This one, and 49 is the last one. So this is the last one. Okay, after this we will end this lecture, and in the next lecture we will solve these questions. Also we will also complete another topic, that is slot harmonics. Thank you, and I will see you in the next lecture. Until then, happy learning.